It is a pleasure for me to introduce Pasa. He is a principal research engineer at Arm. His work is focused on co-design software and hardware building blocks for HPC development on various aspects of the communication middleware and programming models. Prior to joining Arm, he spent 5 years at Oak Ridge National Lab as a research scientist in the CSMD division. There he was responsible for R&D of multiple projects, including the Code Direct and Cheetah, OpenSHMEM and OpenUCX. Before joining Oak Ridge, he spent 10 years at Mellanox Technologies, where he led the HPC team and was one of the key drivers in the enablement of Mellanox HPC software stack, including the OA software stack, OpenMPI, MPI, OpenSHMEM, and others. So he's a recipient of the 2 R&D 100 awards for his contribution to the development of the Code Direct collective offload technology and OpenUCX. So today we'll be talking about recent advances in the HPC network stack on ARM. Yesterday we had a tutorial from ARM, so today you will be supplementing that with additional information. So Pasa, welcome, and please share your screen and you can get started.
Just a second. I will try to share my screen. You should be able to see my slides now.
Yes, yes.
Excellent. Hello, everybody. Diki, thank you very much for providing the opportunity to talk about HPC interconnect research that we're doing at ARM. I'm a principal researcher engineer at ARM responsible for scale-out interconnect research. And I will cover 3 recent projects that we did at ARM related to HPC interconnects. But before I deep dive into projects, I want to give a brief overview to ARM as a company, because ARM is a relatively new player in HPC space. And I just wanted to clarify how ARM works. The real reason why I'm doing this is because people keep asking me where they can get ARM MPI. And I'm trying to describe that ARM is a very different company and we just work in different ways. So ARM is intellectual property company. We design ARM ISA and we design ARM implementation of the ISA. Historically, ARM has been used a lot in mobile market and custom SoC design. And the reason is because you can license our IP, integrate with your secret sauce on your chip, and build special chip for special purpose. For example, you can integrate on your accelerators for interconnect on the chip. You can integrate with own GPUs and so on. So semiconductor partners of ARM license our IP. We have, on really high level, we have 2 types of IP. One is ISA. Essentially, you license our instruction set and you build your own microarchitecture, your own everything. Or you can license one of the existing cores, which is Verilog implementation of the core, and integrate it with your design. Besides cores, we also design interconnects, GPUs. ARM GPU, it's actually most popular GPU in mobile space. Besides interconnects, there is also memory controllers and multiple other building blocks that people may want to have when they build SoC. Our semiconductor partners take this design and they do go to one of the fabs and produce the chip. So in order to make sure that all this process work, we have to work closely with semiconductor partners. We have to work closely with fab manufacturers and our end customers, OEMs that resell the chips or resell a full solution to make sure what we build feeds the needs of our customers. Now, going to MPI question, when people ask, wait, where's ARM MPI? I went to your website, I don't see ARM MPI. The answer is, well, we don't really have to build one because our partners that built our chip, they built MPI. For example, if you go and work on Cray system based on ARM, Cray will provide their MPI. The same true for Mellanox. If you have ARM system with Mellanox interconnect, there is Mellanox MPI available for this. Besides this, there's obviously plenty of open source solution, and MWAPIC is obviously one of the very popular MPI implementations that's known for its optimizations, and it works on ARM just like on any other platform. For whatever reason, okay, it refuses to switch slides. Just to give perspective where ARM used, obviously you know that ARM used in mobile devices, and there is every year a lot of chips shipped with ARM IP, ARM technology every year. Just to give perspective, for 2019, previous year, in total, above 25 billion ARM chips were shipped. To put in perspective, because it's hard to understand this numbers with that many zeros, it's over 700 chips shipped with ARM IP every second. I joined ARM in 2016, and people didn't hear back in the days much about ARM. We attended SC, we had booths, but you did not see any supercomputers. And I remember at previous marks in SC, I was showing this picture of my ARM Mac with a Droid C2 small board. I think it's like $40 board that ARM v8 64-bit. And I'm, hey, this is where actually I'm doing all my MPI development on my desk with this small board. It's where we build various MPI implementation, build SHMEM, ECX, and so on. And just in 4 years, you know, let's look where we now. Last year we had Astra announcement, Astra supercomputing based on Thunder X2 technology. This year, obviously, Fugaku took the top spot in top 500. And the interesting bit is that a lot of the work in optimization, debug, and QA that I did on this small Android C2, most of this work as it is on this large supercomputer. And this is because it's the same ISA. You can run the same compilers, you install the same one of the popular Linux distributions. In whatever works on your small devices, the same way you can run on large machines. It's just bigger chips, more memory, obviously much faster, many more cores, faster memory, and so on. But conceptually, nothing prevented me from doing software development on really small boards. Talking about Fugaku, obviously it was a huge announcement from Fujitsu. Fujitsu is our partner. They build systems, they build custom silicon called A64FX, which is took top spot in top 500. But what is the most impressive bit in all of this, that actually it took top place in 4 other categories besides top 500. It's top place in HPCG, HPLEI, and Graph 500. And you can see in terms of improvement to previous set records, it's ranging from 2x to 4x and so on. So it's really well-balanced machine that works really well for AI workloads, for graph workloads, and for classical HPC, LINPACK in this case, and so on. Now, looking back, again, it's kind of retrospective of some of the events that happened in the past. And it's partially related to the fact that the IP company, obviously the IP for all of these HPC solutions that you observe today on the market, work started much, much earlier. In 2018, we announced Arm Neoverse. It's entirely new line of products focusing on infrastructure servers. And from 2018 to 2020, we saw more and more announcements, our partners coming out and releasing their great platforms, server platforms while we released their Cuping 920, then we had announcement from VMware about support for ARM 64-bit platform. Later in 2019, we announced Neoverse N1 and E1 platform. The same year, NVIDIA announced support for CUDA support for ARM 64-bit platform. Later on, AWS released Graviton 2 server platform, and it shows really fantastic results. Azure demonstrated solutions with ThunderX2, and we see more and more announcements coming out this year. Obviously, the major one was Fugaku. It's mind-blowing what a Fujitsu team managed to achieve in this period of time. It's a machine with a scalable vector extension, integrated interconnect, TOFU. It's really, really impressive platform. I don't know if you have been following the HOTAI announcement. Marvell presented insight on ThunderX3 as their next generation chip. Ampere announced their 80-core and 120-core Ultra Max platform. And Cypher announced that they license Zeus Core. Now, I'm kind of done with coverage, what's going on in ARM and in ARM ecosystem, and I will focus more on the interconnect research that we've been doing. This particular work, we call it Breaking Band, was done in collaboration with my intern. And the questions that we tried to answer with this work was quite simple. So everybody shows these great results on latency, bandwidth with MPI, and we know it's 1-2 micro with InfiniBand. But questions that we ask ourselves, okay, out of this 1-2 micro latency and this ping pong benchmarks on message rate benchmark, if you're talking about message rate, where we actually spend time, how much time spent in software. But we wanted to dig much, much deeper. We want to go beyond software layer. We want to understand how much time it takes for the NIC to access the memory of a PC, how much time is spending on PCIe. When you send message, there's event happens between software and hardware side called doorbell. How much time is spent preparing the doorbell, how much time it takes to make this PC transaction, how much time is spending on the wire. We want a complete breakdown of the latency. Why we want to, why we asking all the questions? It's as a hardware vendor and software developer, I actually want to understand where I have to spend my time optimizing the entire stack. Do I have to spend more on PCIe? Do I have to spend more on my ISA or on the software stack? This is labs setup that we use. This is not your typical MPI research, a lot of wires. It's a ThunderX2 board connected with ConnectX-4. We have PCIe Lacroix analyzer sitting between the board and the NIC itself. Tons of wire to gather log full of this. My intern sitting in the back, very intimidated because so many files. He was concerned that we will break something. And what we get out of this, we can see here. So this overview of our setup that you saw on previous slides, which is we have two nodes. For this particular measurements, we had no InfiniBand switch, but we did have Mellanox force on both sides of machines, Lacroix in the middle of one machine capturing all the traces. And once you capture all the traces, you can interpret where time you spent in each level of stack. This overview of the stack. So you have some sort of user application. Typically, it's under user application, we meant MPI. In our particular case, we used UCX, so it's MPI, UCX. Then you have interconnect driver. You have kernel space, which typically bypassed, and you go to the hardware. And what we gather, it's traces like you see on the slide right now. These are traces from PCIe. This is not measurements from timers that you put in software. This is actually measurements of each PCIe transactions that goes on the wire. So we really can look at, for example, if I want to answer a question, how much time I spent posting the message from MPI all the way down to the wire, I will be looking in the time between time space between different PCI transactions. We actually did both. We measured software time, we measured hardware time on PCI. We make sure that we try to calibrate, see if whatever we observe in software matches hardware and so on. And this sort of information that we were able to extract from these measurements. For example, looking in send receive operation, question, hey, when I send message, when I do post, where I spent and what layers, how much time. So you can see the post time of the post, MPI post consumes 76%, and we have little bit time spent in progress. Why we have progress is because occasionally we have to enter progress function to recycle the packets and so on. The next question was how much time is spent between low-level protocol and high-level protocol. HLP stands for high-level protocol, LLP for low-level protocol. In our case, HLP is MPI and LLP it's UCX. And you can see that actually progress most of the time was spent in MPI function calls, and post time, very little time spent in MPI, and most of the time spent in your middleware. Then we drill down, we look, okay, when I do low-level post, how much time I spend in memory barriers that I have to do in the driver, how much time it takes me to ring the doorbell itself and so on. And in these numbers at the bottom, you can see that actually a majority of the time was consumed to PIO copy, which is this is the function that triggers the doorbell to the NIC. So once you have this information, you can go and dig into the software stack and optimize lower level or high level. Now, in this slide, we looked on not just software part, but we also look on the network part, wire, how much time is spent on PCI and so on. You have different transactions. IO is associated with PCI in this case. And you can see that between low-level and high-level protocols, split on your time is 50-50. A lot of time actually spent on PCI transaction. Switch latency relatively low. In our measurements, we use one switch. And wire in network wire latency, it's what really dominates the transaction. On the target side, again, we spend that between initiator, sender, receiver, a lot of time was spent on the target. This is because of progress. And you can go, again, having this data, go and optimize your code on the target. CPU and PC was 50-50. And we noticed that on the receiver side, most of the time, and PC was actually spent in transaction from the NIC to the memory. So key contribution of the work, we did measurements with PCI and PC Analyzer. We did measurements in software. We made sure that all results are aligned. We actually built an analytical model for this. And we checked the analytical models and we saw that we have around 5% margin error when we compare to numbers we gathered with PCI. We have total breakdown for a relatively simple communication transaction. And now people can take this information, go and optimize their software or hardware layers. We also, as part of the work, we collaborated with Marvell, Melnox, and NL. And I want to thank Giri, Yosin, Pavan for helping us with during this work. It was really exciting. It was a really cool experience to drill down the network latency all the way from MPI level down to the bare metal and actually to what happens to the wires. So the next work is very recent research work. It was just published at CCGrid recently. This was collaboration with University of Knoxville, Tennessee. Donk is my intern. We worked on this last year. And with, the research was about, hey, we have Fujitsu machine coming out. It actually was before we had product machine. And we collaborated with Fujitsu on this as well. It's kind of important. bit, because I will show results on production Fujitsu machine, pre-production, sorry, Fujitsu machine. But we want to see how we can use SVE, scalable vector extension that were introduced at Arm relatively recently, how we can use for optimizing network stack. And this research included a lot of different components. We had to work with new instruction set. Before we didn't have hardware when we started the project, we worked on emulators and simulators to essentially estimate the results. And eventually we actually work on real machines with SVE on this. So brief, really high level review for SVE. I'm sure it was covered on the tutorials yesterday to some extent. Scalable vector extension is length agnostic ISA that IP providers can design SVE with different sizes, but software that you develop on top of SVE doesn't really have to be aware about the size. It's a bit a different semantic compared to what you saw in existing ISA, but roots of the semantics goes all the way back to original Cray machines with large vectors. It has vector itself, and you have predicates that indicates what part of vector you use. And using predicate, you can play with what parts of registers you want to use for this instruction, for the instruction. So when we thought, okay, how are we going to apply SVE? So we have MPI pack-and-pack operations. On the SVE side, we have predicate really large vectors that we can use for optimization of packing and unpacking. When we look in MPI data types, you actually have contiguous, non-contiguous data types, and SVE has very rich semantic of scatter-gather instructions that you actually can use a scatter-gather ISA of SVE to serialize the data from non-contiguous buffer to contiguous buffer. And obviously you can do MPI reduction operations. As this like overview, for example, for MPI gather, local gather, historically how it's been done, you had a loop that going over the, let's say, column of the matrix and copies elements of the column into contiguous vector to send the data. With vector implementation using gather, you can just provide indices of the vector of the column and pack it into contiguous buffer. And this level of optimization, these optimizations that we have been doing with this code. We did runs with Arm-E, which is simulator. Before we hit platform, we did evaluation with Gem5, which is simulator as they can use to simulate ARMv8 and SVE. Everything, Arm-E is available from website, from our website. Gem5 is open source. We have streamed models for SVE and everything. So just Google and you can get it from GitHub, I believe. But we were lucky because at the time, Fujitsu guys started to bring up Fugaku, and we worked with Fujitsu engineer on evaluation of our implementation on pre-production system. So we looked into, on Fugaku, we have support for up to 512 bytes. We looked at different vector sizes. We compared it to optimized version of memcopy, compared to SVE, we compared it to no SVE at all. And we show that very substantial speedup can be achieved with SVE instructions for reduction. And we actually compared it to regular memcopies that doesn't do any reduction, just to understand what is our top limit for in terms of memory bandwidth. And you can see it's actually not far off. And it's great, 4 times faster when you compare to non-SVE. And this results from actual silicon. This is not simulation. If you go to the paper, you will see Arm-E instruction count results, Gem5, and all the other information how exactly we structure these experiments. Similarly, we did studies for MPI scatter-gather. And again, we observed huge speedup with SVE when you use SVE instructions for packing non-contiguous data. and we compare it to when we have the blue line, dotted line, non-gather, it's actually using memcopy that optimized memcopy with VSV instruction as well, but because it's not exposed to this notion of non-contiguous memory, it's just loop of memcopies, and as a SVE, it's much more optimized because it actually leverages SVE gather instruction. So key contribution from this work is we showed that SVE can be used for optimizing network layers and MPI specifically for contiguous, non-contiguous data. I don't think it's ends there. There's many more opportunities for acceleration in MPI using SVE. And what is even more important, we actually show to developers how this sort of study can be conducted even if you don't have access to SVE machine. You can do it with simulator, you can do it with emulator developed code. You can play it with different vector sizes. For example, our Gem5s, we evaluated really wide vectors as well. Now, the next work is actually a preview of something of research that was done by Arm in collaboration with Los Alamos National Laboratory. This very fresh research, actually, this paper will be presented this Friday at Smoky Mountain Conference. So I just give it kind of very short preview what has been done. If you want to learn more, please register to Smoky Mountain Conference. They will have our slides, and first paper will be published later in the year on this. So as part of this work, we start to explore that, hey, we have this all new memory solutions that people call PMEM, but essentially it's byte addressable persistent memory. If we have PMEM, how we will build our storage system if you want to optimize it for HPC? And to answer in terms of build, I mean how in terms of software programming models will interact with this memory. Obviously, you can use file system and take legacy approaches with POSIX, but we really wanted to explore how we can change programming models to fit better this new persistent storage. And we found an answer with PGAS, and specifically OpenSHMEM, that defines partition global address space programming model. Since storage is byte addressable, it actually looks very, very similar to regular memory, with the differences it has this property of persistency. So we took OpenSHMEM and we extended OpenSHMEM programming model to support persistent addressable, byte addressable storage. We built a solution using RDMA, and to make it even more interesting, we thought about all these new solutions that come in with DPUs that Gilad talked earlier today. As a name for this, it's SmartNICs. That essentially you have a NIC that ARM cores attached to it and some memory, and potentially this memory can be persistent memory. And we built software stack for DPU and software stack for OpenSHMEM clients. It's based on UCX, both sides based on UCX. The server side doesn't use SHMEM. We call it talks native SHMEM, but actually implementation doesn't use SHMEM API. It's just directly implemented server on top of UCX. We use DAX extension in Linux combined with PMEM. We use some on-demand paging, and there is often information in the paper itself how we implement it. We had to go and update kernel to support PMEM on ARM. We had to work on BIOS level to add support for NVDIMMs. We introduced entirely new set of APIs for SHMEM that actually changes SHMEM greatly. Now we have a version of SHMEM that supports server client semantics. It also supports attachable and detachable remote storage. And we also added support for multiple levels of consistency, just in case if somebody want to use a semantic to build some sort of cache server based on PMEM sitting just before the slow storage server, and occasionally dumping all the files and data back to from PMEM back to slow storage. As I mentioned earlier, because it's byte addressable storage, SHMEM communication semantics was perfect fit for what we want to do, because you can use pretty much regular put and gets to address the memory. So once you attach remotely addressable storage, all the rest of application actually looks like regular SHMEM application, put, gets, reads, and so on. The only difference is that now the storage is backed by this persistent memory, and we have some new semantics that lets you flush it to different level of persistency with the storage. These some preliminary results. I'm not going to into details here. It will be shown in SMC conference. Will be shown later on this week in details. But we compare to NFS and classical POSIX, and it shows that SmartNICs with NVDIMMs scales really well in terms of weak scaling, and it's nearly linear scaling when you compare to NFS or classical POSIX semantics. This work was done at Arm in collaboration with Los Alamos. We open source the entire stack. It will be available on under OpenSHMEM project at UCF. I provided link to Git repo. We didn't push the code yet. We'll push it on Friday when we present the paper. For more details as a reference, please go and read the paper. And I would like to acknowledge our partners from Department of Defense and Los Alamos for supporting this. We also got a lot of help from Gilead and OneWang from Mellanox with helping us to bootstrap software stack on Bluefit for all of this. Thank you very much. Seems like I'm running over the time.
Asad, thanks. I think there is one question in the QA box. If you can please take a look.
Yes, I'm trying to read it. So ARM partners can license only their ISA without licensing ARM core designs. Those do their own core implementation. The answer is yes. Customers can license just the ISA and do completely custom design of their SoC. They may decide to license some other bits of our ISA as well. For example, they may build custom core and license our on-chip interconnect, for example. Is Fujitsu on-core A64FX Fujitsu on-core design? Yes, it is a custom core designed by Fujitsu team. Was there a proposition of licensed ARM ISA? I'm not sure if I get the last one. I'm not sure it will remain under proposition of licensing ARM ISA. I guess you can probably ask our sales guys what kind of propositions they have, but it is a pretty different model for CPU company. But again, you can license different components from ARM, core, interconnect, memory controllers, SMMU, you name it, and based on this, build completely custom chip. Any more questions?
No, I don't think there is any other question. So